Everyone, and welcome to this video short where we are going to discuss graph traversals, that is specifically searching on a graph. We'll look at brute force search and a greedy search. So let's look at the problem setup first before we begin. So searching on a graph, right? We have our graph set up here with nodes and edges. And the idea here is that we will start at some point and we wish to identify or find a particular location or item on this graph during the search itself. If we were going to do a brute force search, we would exhaustively search the graph until we find what we're looking for. The pro with a brute force search is that you will eventually get to a solution. You will find the best solution. You will find it because it's an exhaustive search, thus the name. However, you don't necessarily perform the search in a well-informed or efficient way, so the time complexity for brute force or exhaustive searches can be quite high. Using a greedy approach, we attempt to have a more methodical and well-informed searching strategy to reduce the time complexity and make the search more efficient. Greedy algorithms employ heuristics to allow us to accomplish this. One common searching algorithm on a graph that is of the greedy variety is a best first search. So let's go ahead and take a look at this. The idea here with best first search and with greedy algorithms in general is that we want to make the best decision we can every single time we're faced with a choice. This is the greedy choice property. And the idea here is that we're not necessarily going to be able to look at finding the optimal, globally, that is, optimal solution. But what we're going to do is look for locally optimal solutions and make those choices when we're confronted with them. The goal is, of course, to get to a solution that is optimal globally, or at least near to globally optimal, but it's not going to be guaranteed. So in this example, let's assume that we are going to start at the node Arad and attempt to find or search for Bucharest. And we want to get there in the shortest path possible. So let's go ahead and try best first search. The idea here is with the values on the edges representing a straight line distance, we will choose to traverse from node to another node toward our goal of Bucharest using the shortest length possible. And we'll do this by sequentially making the best choice available to us, the greedy choice. We're going to be greedy on edge length, and edge length here is represented by shortest path distance. Greedy in the sense is we want the minimal path, so we're going to take the minimal edge or the closest point toward our goal. Again, this is going to be a locally optimal choice, not necessarily global, but we hope to find a solution that is close to globally optimal. All right, so let's begin the search. Here's the straight line distance from Arad, right, to some of these other points. And if we blow up the graph here, we see that if we start at Arad, we have 3 possible points to traverse to. We have Sibiu, Timisoara, and Zirant. Each of them have corresponding lengths associated with them, or edge values. And again, in this example, the edge values are the straight line distance toward the goal. So Sibiu has the shortest estimate for straight line distance to our goal, so we are going to traverse to Sibiu. After that, we open up a number of other options to traverse to. So we can still traverse to Timisoara and Zirant, but we can now also traverse to Făgăraș, Oradea, and Râmnicu, Vilcea. All right, and each of these again have values associated with the distance from that node to the goal node of Bucharest. So given our options here, right, we don't want to go back to Arad. We have 176, 380, 193, 329, and 374. So 176 is still now the closest node to Bucharest. So we will traverse there next, again, assuming that each of these other points are further away. Now note again, this is not going to guarantee us the best path to Bucharest, but it is pretty intuitive way to traverse the graph quickly. Right? And in fact, when we do traverse Tabacras and Fagras, and explore its neighbors, we find that Bucharest is one of the neighbors, so we can then arrive to our goal node. We have found Bucharest. The shortest path the path that we chose to get there was Arad to Sibiu to Fagras to Bucharest. All right. So, how long does this take? Well, in general, greedy methods give us really fast solutions that are not guaranteed to be globally optimal, but are generally pretty close to globally optimal. Here, the time complexity is based largely on the number of branches. Here we have b to the m, where m is the maximum depth in the search possible. Right. So again, think of depth as tree. That is how far you can search any of the branches within this graph. Again, it doesn't necessarily produce an optimal solution, but it can give us one that is pretty close pretty often. Right. There are a number of different variations of greedy searches on graphs and other types of searching algorithms on graphs as well. Another one that we'll explore in this PowerPoint deck is known as A-star search. An A-star search takes another step within this greedy philosophy and updates the estimate of the total cost to get from your source node to the destination node by using a heuristic to estimate the distance from the node you are currently visiting to the goal node, but then you update based on how much distance you've traveled up to that point. So it gives you more information so you can make a more well-informed decision at each step. So I encourage you to read on about A-star search, this extra variation of a greedy search on a graph. Thank you for joining me in this video short, and I hope to see you in the next episode.